So how's everybody doing? Today's day 2. Thumbs up if you're feeling good. Yeah? Okay, great. That's awesome. Today we're going to go through the fundamentals of deep learning. This is a topic I'm very excited to teach. It's because of a few things, a culmination of a few things. Firstly, I found at work there's a lot of hype around deep learning. How many of you have experienced that hype at work? Oh yes, there we go. How many of you have heard this sentence, or an analog of it? We should just throw everything into a deep learning AI and let it spit out the answers. Ooh, there you go. Yeah, I've heard that at work as well. And frankly, it reflects an ignorance on the part of those who mentioned that statement, that they're thinking of machines as thinking beings and not really just the machines that they really are, right? So part of this, the reason I put together this tutorial was in response to that experience. I wanted to make sure that I, at least myself, knew at a very deep level what exactly deep learning was all about, and that on the other hand, I was able to use the same material to communicate to others what exactly is going on underneath. So in other words, it's a little bit of demystification of what goes on behind that. Now, there's another reason that I put this together, and it sort of mirrors my own learning journey into deep learning, in which I started with the frameworks. And how many of you know some framework, like Keras or PyTorch? Great. Like, if you've used it and you've done productive things with it, that's all good and everything. But sometimes there's that nagging itch, right, that says, well, what exactly is going on behind the scenes, right? And that's the second motivation for why I put together this material. That is to demystify what goes on behind a framework, a deep learning framework. And in fact, if we have enough time today, we may be able at the end of going through all of the fundamentals, we may actually be able to write our own little mini deep learning framework. It's actually, if you know the components, it's not hard to write a simple MVP version of something like Keras or PyTorch. It's really not difficult. But it takes knowing the fundamentals to be able to do something like that. So we may be able to get to that today. Now, this is a tutorial that I've rehearsed in multiple settings. I've done this one-on-one with colleagues, and we only took 2 hours. We only took 2 hours. But of course, we didn't do a lot of live coding exercises. We went through mostly conceptual things. So the baseline time that I've got for this is 2 hours. If you all are great with code and everything, we actually may be able to be done in less than the full 4 hours. I tried this at the Olin College of Engineering. Thanks to Alan, he let me use his students as guinea pigs, basically. So test drove it there, and we, together, he and I taught one half, he taught the latter half. That whole thing took about 3 hours in total, got some feedback from them. I also tried this on a trip. I went to Shanghai, and I visited our colleagues out there. And that one was a challenge because I had to do I started out telling them, I'm going to do everything in English. And then I ended up speaking half the time in Chinese instead. And that was a challenge because there's tons of linear algebra terms that I didn't know in Chinese, and they filled in the blanks for me. So we took 4 hours that day. So that's the upper bound. That's the upper bound that I got for the amount of time we'll need. My goal, of course, is not to fill the time. My goal is to give you the fundamentals, and whatever time we finish is whatever time we'll finish. And if we finish early, you'll either get to have lunch early, beat the lunch crowd, or we can talk more, Q&A and whatever after the tutorial. All right, so as I mentioned, the goals behind this tutorial are to, number one, demystify what goes on behind the frameworks, right? So what goes on behind PyTorch? What exactly are they doing when they say optimize? What exactly is a dense layer, et cetera, okay? The second one is to give you the vocabulary, some vocabulary to read some of the literature. If you already know the vocabulary, then that's great. If you have only a fuzzy picture between what we mean by a layer or what we mean by a dense layer, convolution layer, et cetera, well, we won't get to convolutions, but at least behind the dense layer, dropout, et cetera, then my goal is to make that connection clearer. And if you don't have that connection already, my goal is to make that connection for you. And finally, I think it's really important to be able to connect that vocabulary to actual code. Something about learning this whole deep learning business, for me at least, was once I coded it up, right? Once I implemented a very simple feed-forward neural network in pure NumPy code and did the optimization behind the scenes, suddenly deep learning didn't feel that deep at all, right? It felt a lot more accessible, and it was a lot more approachable, and I could catch a lot of the nonsense that people were spewing in our day-to-day conversations and just shut them out if I knew they were going off on a wrong tangent. And so, yeah, the side product of knowledge, of course, is like a clear mind, right? And so philosophically, hopefully, this will help with your day-to-day interactions. You'll be hopefully less awkward than I am when I'm like dealing with people who I know are spouting nonsense. Hopefully, you'll be a bit more diplomatic. Let's just put it that way. All right. And at the end of it all, I hope you'll find that this was really just an excuse to teach. You'll find that at the end of the day, for me, this was an excuse to teach what automatic differentiation is. And automatic differentiation is the core of all, is part of the core of all deep learning. And we'll get to that, but that you'll find out, oh yeah, all of this is just auto-diff business, okay? Cool. So to get started, I'd like to invite you to open up your notebooks. We're going to go through a bunch of models, and today's agenda is structured like something you'd see up there. Basically, we are going to not start with deep learning. We're going to take all of the components of deep learning and use it to study linear regression. And I have a really good reason for this. If you were at yesterday's Bayesian tutorial, you'll notice we spent a long time talking about the beta binomial model. And that's because it's a simple model, it's easy to grok. But at the same time, it's one of those models that you can really build out a lot of core knowledge on. And once you've got the core concepts on a nice anchoring example, suddenly everything else looks like a parallel, okay? So that's why we will be studying linear regression for approximately 2 hours, all right? We'll take all of the components of deep learning, go into a deep dive. If we're fast, we'll maybe take an hour and a half, right? And once you've gotten that core knowledge on the core components as it applies to how you do linear regression, you will see it. I'll draw it out. There'll be lots of figures for you to see. Everything else transfers over just easily, all right? Okay, so how are we doing? Everybody got the notebooks up? Thumbs up? Thumbs up? Okay, great. So, linear regression, the thing that we learn in our undergrad statistics class. What's the equation form? Any volunteers? This is a giveaway. Y equals mx plus c, right? Y equals mx plus c. What we're saying is that the thing that's of interest, y, is nothing more than being controlled by the data x and some parameters that we can tweak to get that model to adjust we can adjust the parameters m and c such that we can get x's to be transformed into y, right? That's all we're saying. It's a linear combination of our x's. Now, where do we use linear regression? Where do we use linear regression? Everywhere, yeah, that's right. We use linear models all over the place, right? And why would one want to use linear models? They're simple. They're easy to interpret. Yes, exactly. What else? Pardon me? Practically speaking, they're good enough to do what we need to do. Right. What are some of the disadvantages of a linear model? Those are the advantages, right? That's why we use them. Why would we not want to use linear models?
The world is not linear.
Yeah, but if you zoom in hard enough, right, everything is approximately linear. True, but yes. So the world at a bigger scale is not always going to be linear, right? So maybe there's something there. What else?
A lot of data assumptions.
Yeah, if And if you do these things like canned statistical procedures, which I ranted about before, ranted against, sorry, before at PyCon this year, our LM packages in R or stats models, linear models packages, we're putting a whole bunch of assumptions on our data, which may not necessarily be true, which again motivates why we really should think hard about what our data are, how the data generating process is, how we write down our models. Okay, any other disadvantages to linear models? All right, if we say that the world isn't necessarily linear, I didn't put this question in our discussion, but if we say that the world isn't exactly linear, what are some tricks we can use to get around the fact that there's nonlinearity and still yet use a linear model? Just want to make sure this knowledge is out there.
Well, we make the linear regression around our operating point, or around the point that we want to maintain a steady state.
So we zoom in, basically. Okay, yeah, okay. What else? Back there? Of your X data, so you can do like polynomial regression by doing the X square terms or that sort of thing. Anything else?
Do something like PCA to reduce that another way of like getting a new feature to look at.
Maybe, yeah. So we figure out what the if that of course still has a bunch of linear assumptions inside there, but if those linear assumptions generally hold, then yeah, maybe we could do something like that. There's a really great talk. I think it's a PyData talk that says, don't use deep learning. Use linear models where you can, and here's how you can actually do a whole bunch of tricks to make your data work with linear models, right? If you have time series data, et cetera. All right, cool. So those are, and I'd encourage you to check that out. So let's move on. Let's think about, let's start with some simulations, all right? Let's start with some simulations. So I'd like to invite you to move down to this part over here in the student notebook, okay? And we're going to try a little exercise which lets us, which will give us simulated data to play with and will hopefully illuminate some ideas that we'll want to be able to automate with programming, all right? So go ahead, do this exercise. Put in a value for, some value for W and some value for B. These are the parameters of the equation, linear equation, and write the linear equation down and make a plot. And I will be coding along with you guys as well. So go ahead, make some noisy data. And you should get something that looks like that. Do you all have the plot? Thumbs up if you do. Okay, cool. If we were to use this linear model, if we were to use a linear model and take a really bad guess at what the parameters would be, let's see how bad of a guess we can make, right? So, because if we start with a guess at the parameters of the model, but we're wrong, we'll want to be able to find some way to tweak those parameters in an automatic fashion, right? So I'm going to have you put a really bad guess inside there. So fill in a bad value for W and fill in a bad value for B. Okay, so everybody got their really bad model? Yep, looks something like this? Looks something like that? Okay, cool. How many of you were able to get it completely orthogonal? Take some solving of equations to do that. I don't know how to do that right now, so I'm not going to show that. Now, I got a question for you. How do we know this model is bad. How do we quantify the fact that it's bad? Talk with your neighbor for a minute. I usually do this to help people network with each other, so talk with your neighbor for a minute. How would you quantify how bad this model looks? Introduce yourself, network a little bit. Okay, how are we doing? Do we have an answer? Someone, a brave soul who's willing to like volunteer something. How would you quantify how bad this model is? Back there.
The average of the distances all points
To the line? Yeah, okay, so we can look at that. That's what we might call the average absolute error or mean absolute error, right? So that's one way of quantifying it. So let's see how that looks visually. I got my bad model. It's a line, all right? Actually, I'm going to make this a little bit bigger for you all. So let's use a thicker pen. So we got a line, okay? And that's our really bad model. Okay, and we got our data, and our data are in blue. And so what we might do is we would say, I got that data point there. Let me draw the distance from that data point to the line, and we'll call this the absolute error. And we'll do it again for the next data point, the next data point, the next data point, and so on. And we'll have a bunch of vertical lines that tell us the absolute error, the vertical height, from our model to our data. Are we okay with that? So far, so good? That is one way of doing it, and the way, effectively, all this is just a difference between the errors and the model predictions at those x values, right? So that's one way of doing it. And we would call this the mean absolute error. And this, by the way, is a completely valid way of quantifying how bad a model is. A more common way, it's not common though, right? More common way is to actually use the mean squared error. And once we go into the optimization section of this tutorial, you'll see why the square becomes kind of important, right? There's nice convex properties that we can take advantage of. But so before I derail myself into that topic, let's just say that we're going to define the loss function as the mean squared error instead. And so all we do, so if we label these errors as E1, E2, E3, E4, E5, and E6. The mean squared error, well, getting notifications there. Mean squared error I have my friend Joanne in the house. Joanne, can you ping Zach to stop pinging me? Thank you. And we'll define that. No, there we go again. E1 square plus E2 square plus E3 square, etc., all the way to En square divided by n. That's the mean squared error function. Okay? Now, we're going to try, I'm going to have you try implementing this in NumPy code. I naturally have on the screen the answer. You can always copy it over if you'd like. But I'd also encourage you to try to do it as much as you can from memory using NumPy code. All right? We're going to implement a mean squared error function. And this will be our loss function for the linear model. it should take in y true, that is the actual data, and the y predicted, the non-actual data, the model predictions as the arguments, and return a single number that tells us what the predicted value, what the error of this model would be, right? And I'll code along so that I can pace myself to what you would be at. Okay. On the left is the instructor version of the notebooks, right? And I have a one-liner that has everything written there. On the right, re-implemented the whole thing, but now, breaking out what the individual components are. This error term is what we would call the residual term, right? So we'll basically, what's the errors between, it's the model prediction minus the truth minus the model prediction. Then we square it, and then we take the mean. And that's what we call the mean squared error. And wanted to check with y'all, what's your model's squared error? I have 365. Anybody can beat that? Huh? 30. Only 30.
709.
Oh, 709. How did you do that? All right, so he had something close to orthogonal, I think. So, cool. Now what we're going to do is we're going to do a manual optimization of the model. You'll notice if you go to the next cell, there are two knobs that you can turn. There's a knob for the weights parameter, and there's a knob for the bias parameter, or the M and the C parameter. And I'd like you to go ahead and try optimizing this model by hand, right? And tweak the sliders until you get something that fits. And while you're doing that, observe how the mean squared error also changes. Okay, so how are we doing? Thumbs up if you've got your tweaked model already on the screen. You have something like this guy. Okay, wait for a few more people to finish this exercise. If you need to, you may need to, because of the values that you've chosen for your W and B, you may need to adjust the min and the max on the sliders in order to get your interactivity working. All right, spot check how many of you are done. Thumbs up. Okay, so we're about quorum. I usually move on at about 70%, 60 to 70% of the crowd being done. All right, so now I'd like you to discuss with your neighbor. When you were optimizing the model, what were you looking out for? I know you already knew the correct answer. But if you assumed and put yourself in the position of someone who did not know the correct answer, what were you taking advantage of in order to get the parameters into the right ballpark? Talk with your neighbor for a minute. Hey, I hear the conversation dying down. Like to hear back. Do we again have some brave souls who are willing to share what were they looking out for, right, when they were optimizing the model?
After over and undershooting a bit, tuning both parameters like back and forth, but tried to get the intercept to line up and then do the slope.
Yep, okay, cool, all right. So you made sure the intercept was okay, and then you sort of did that. What else were you looking out for? The error? What about the error? Right, okay, so we're saying we want to make sure the error between the model, the error as we've defined, the mean squared error. You could, by the way, do it with mean absolute error, totally okay. The error as we've defined it, we want to bring it, we want to tweak the numbers of interest, turn the knobs such that we eventually reach this minima point, right, that we're interested in. And that minima point, if you hear the term minima and you hear the term parameters, that first thing that you should be thinking about at this point is optimization with you taking advantage of derivatives, right? So that's the detour we're going to go into first, all right? We're going to talk about gradient-based optimization. But to talk about gradient-based optimization, I have to know first where in the crowd who in the crowd remembers how to take derivatives with respect to a single parameter. Can you raise your hand? I want to make sure this is like evenly distributed enough. Okay, great, cool, good. All right, so, well, then let me make sure I'm going to have you all make sure you're not looking at the answers below. I'm going to give you an arbitrary function, right? It's going to be a squared x function. And I'd like you to, on your papers, in your minds somehow, take the derivative and find the minima of this function. F of x is x squared plus 3w minus 5. So can you analytically find out where the minima should be? So go ahead, do your math, talk with your neighbors if you need to. We'll spend about a minute or two doing that. And if you need paper, I have paper here. There's pens up front as well. Feel free to grab some. Papers here. Go for it.
There instead of
Thank you. Yep, question up there? Sorry? Sure. I think people have your answers already, right? Thumbs up if you do. Okay, cool. Any volunteers? What value of x minimizes f of x?
So if you take the derivative and set it equal to 0,
Okay.
when the slope is equal to 0, that if given one answer should be the minimum.
Cool. So then let's take the derivative. What is the derivative here?
It's going to be 2x plus 3.
Okay. And we say the next thing we need to do is set that derivative to be equal to 0 because at the minima we know that the slope is equal to 0. X is negative 1.5, and I'm sure everybody got the same answer. And then how do we validate the fact that it is a minima? Second derivative, what is the second derivative? Second derivative is 2. This is always greater than 0. So that means there's a smiley face. The curve is a smiley face, and therefore it is the point we found is a minima. And if it was negative, it's a frowning face. and therefore the point that we found is a maxima. Cool. Elementary stuff, right? Okay, so we're able to, with simple functions, analytically find out what the derivatives are. And this is okay for like if we've got this kind of equation. We're doing an analogous thing with the loss function. Now, I've written this for myself 3 or 4 times now from memory, and it takes me about 10 minutes to make sure I've got everything done. So I'm not going to do it live, but I'm happy to do it during the break and flash it up on the screen. But if you do the derivative of the mean squared loss with respect to a linear model, we can prove that it is always a smiley face with respect to each of the parameters. It's a smiley face with respect to W, and it's a smiley face with respect to B. And what that means is if we we can actually then analytically solve the equation and say at that minima, what is the value of B and what is the value of W? But if we had a more complex model, well, good luck to us then, right? Like if we have a more complex model, if you love doing algebra, go do it, right? But I don't love doing algebra, and so I'd rather have a computer do the hard math for a lazy programmer like me, okay? And so that's where we get into this notion of how do we write a program that automatically helps us navigate this curve until it finds the minima, right? And in order to do that, we need to have a program that knows how to take the derivatives of whatever arbitrary math function that we've written. So how many of you have heard of automatic differentiation? Automatic differentiation is the core engine that powers all of the optimization routines in machine learning. So it's a very, very foundational tool. Over here, what we're using is this package called JAX. JAX is the 2nd generation autograd. Autograd, the 1st generation, is basically a thin layer around NumPy that lets you take the derivatives of arbitrary NumPy code, okay? And JAX is just the 2nd generation that did some things that I wanted to do and attempted to do, like making JAX work with GPU code, like CuPy. I got halfway there and then realized, oh, these guys, the guys who taught me deep learning, they're actually writing JAX at Google, and they've released this as a open source project, research project that they're getting people collaborating on, and JAX compiles to GPU and TPU. So, well, okay, I don't have to do it anymore. I don't have to go wrap CuPy anymore. But I did successfully wrap CuPy. And if anybody's like interested, we can talk about that afterwards. It was a very educational experience. But yes, anyways, if we minimize f of w analytically, we get something like that. We have the smiley face. We can make sure we're at the minima. On the other hand, we can actually write a program that lets us do this, right? So what I'm going to have you try to do now is to write that f of x function or that f of w function as NumPy code and write the derivative, and then now we're going to see how we can make a program do all of that optimization, do gradient-based optimization to help us find the minima. Okay, so I'd like you to spend a minute or two on that, working on this exercise over here. And I'll be typing along on the screen so I can pace myself once again. When you're done, give me a bored look so that I know that you're ready to move on. I'm hoping you go up to about there, and then we'll talk about what we need to do next. Okie dokes. Okay, so what we've got now is a starting point on the x-axis. Actually, I'm gonna switch back to drawing mode, because I think this is important to visualize. So we've got our parabola, and you've picked a starting point on the x-axis. That corresponds to some value up there. So what we're going to be doing next is writing code that says, compute the gradient of this, compute the gradient here. And we know that the gradient points this way, okay? Compute the gradient at that point that we are on the x-axis with on that point on the curve with respect to that value at the x-axis. And we're going to take a step in the negative gradient direction. Okay, so we're going to move from the red dot to the blue dot. How do we do that? Well, we compute the negative of the gradient, multiply it by some really, really small number so we don't take excessively large steps. And then we move down and we say the new value of that we're interested in is going to be this thing on the x-axis, right? So we reassign our value, our starting value to the new value of interest, okay? And we do that many, 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 many times until we hit the bottom of the bowl, okay? I'm going to switch back to code mode. I'd like you to code along. So we'll iterate, say, 1,000 times. We've got our starting value of w. So we're going to reassign the value of w. W equals w minus the gradient of w, the gradient taken with respect to w, times some small number. Okay? And let's execute the cell then. Right. Let's execute the cell. And I'd like to ask, how many of you got back some number that's super duper close to negative 1.5? Right. We should all converge on the same answer. Now, what I'd like you to do is actually, I'm going to impromptu add in this little exercise here, a few exercises here. I'd like you to change the training routine. So this, by the way, okay, maybe I should backtrack a little bit. This over here is the programmatic routine that does what we were doing by hand, right? It is the thing that programs the computer to go down the hill until it reaches the bottom of the bowl. It is the routine that does basically the fancy math for us lazy programmers, all right? So what I'm going to have you do is change a few things about this training routine. You'll notice we've taken small steps. What happens if we don't take small steps? What happens then? What happens if we only run this program for like 50 steps? What happens if we run for 2,000 steps? So I'd like you to take 2 minutes and go run a few experiments on that, okay? I'm hoping you have had some time to run a few experiments. How many tried this thing where you only ran the program for like 3 or 5 or some small number of iterations? What happens? Well, are you closer to the correct value? You're way off. That is surprising to me. Okay. The error, sorry, so what's the starting value that you had?
Should be negative 1.5. Oh, the starting, 13.4.
13.4. So as you run for like a few steps with small step size, do you get closer to negative 1.5 or you get further away?
Oh, I got a little closer.
Yes, you should. That should be what happens. Yes, so it does get closer, though it's not, but it's still far away, right? Yeah, okay, cool. Did you try something?
I tried like 20 and 50 per iteration.
Yep, and did you get?
I got closer, but I didn't get to the global minimum.
Right, exactly, right. And that's exactly what should happen. Now, yeah, go ahead.
Interesting. I changed the step size to 0.5.
Okay,
And no matter what I did, it converged on negative 1.5 all the time.
okay, with 1,000 steps.
No matter what the steps were. And no matter what the starting point was.
Ah, yes. Yes, that's a very unique property, yes. Now I need to switch back to drawing mode. How many tried step size 1? What happened? Pardon me? It never converged. Did you print out what exactly the new values of W were if you try step size 1? Here. take a look at what happens here. I mean, try it for yourself as well. If you do step size 1, that means you just don't take a small step at all. What happens is you're actually just ping-ponging between two values, right? So I'm tempted to switch to drawing mode, but I think you all can visualize what's going on. You start at some height and you just ping-pong right over to the other side at the same height, and then you ping-pong back, right? That's what happens when you do step size 1. And so what's neat about the parabola, at least the parabola case, is if you start at some point and you go to step size 0.5, you're just taking half of the distance, so really you'll hit the minima straight away. And this is kind of a hack that you probably could figure out analytically, right? If you did the right thing. You'll hit the minima and then realize, oh shoots, I don't have to move anymore, and then you're at negative 1.5. Okay, cool. How many tried a step size greater than 1? What happened?
You get not a number.
Yeah, like let's try that. You'll notice you do step size greater than 1, you suddenly are overshooting and you're going to actually a higher point, and then you go to a higher point, and then you go to a higher point, until at some point you should get not a number, or you'll get negative infinity, and then, or positive infinity, and then you try to multiply that, and that's just not a number.
You could go, I could go to about 1.51, and then I go above that. You could go above 1.
You could go above 1 for a little bit of time.
No, it would converge.
It would converge?
Yep.
I'm very surprised at that, because if you try this with 1.1 here, it doesn't converge at all. I would encourage others to verify that for me as well.
Yeah, the ending value isn't negative 1.5.
No, it doesn't reach the correct value,
Right.
but it returns an answer.
Oh, okay, sure. So the fact is, okay, that is correct then. Right? You don't hit the correct value. You will not converge on the correct value. You will in fact just explode. Like the value will explode. It's like dividing by 0. Okay, cool. So this is a program that we just wrote, you all just wrote, to take a fixed math function, f of w, implement it in a certain way, this guy over here, and to optimize it by gradient descent. Right? So congratulations, you now know gradient descent. You know one component of a deep learning model. Okay? That's the optimizer. Okay. So if I have a math function, f of w, or f of x, and I have to write the gradient function for that function, and I have to do it for every new model that I write, that's kind of not very, yeah, it's not very, I don't know, I wouldn't want to do that for every single math function I wrote, okay? So that's where a package or an automatic differentiation system comes into play. An automatic differentiation system, what it's able to do is to parse your code and figure out what the analytical derivative form should be in code. Okay? This is, by the way, not exactly the same as taking derivatives by minute differences. Okay? This is not the same. Okay? This is, you are getting an exact derivative for your function, but it is implemented as another function. And in this case, it is a Python function given back to you, which is the gradient function, okay? So we'll see how we can use JAX, or if you're using the first version, AutoGrad, to write that. Okay, so I'm gonna take this guy and sort of just rerun that like this. So what changes? If all that changes is we use a function from JAX or AutoGrad, and that function is called grad. So it's that first line up there. So if you look at what's going on up there, we can actually create a function called df. Don't mistake this with a data frame. You create a function called the derivative of f, df, by passing f through the grad function. And what that returns is another function, and that function computes the exact derivative. So I'd like you to run that cell below. Pick the same starting w as you might have started with, right? And you might see a progress bar that shows up, and you should get back something that's really, really close. Everybody got that? Everybody got that? Cool? Cool. All right. Cool. So we have basically the ingredients for optimizing a linear model, right? We know that the loss function is a smiley face. Okay, so we know that we can find a minima. We know that we can initialize values, W and B, at a certain place. We just now need to figure out a way to take advantage of an automatic differentiation system to get back the correct values of W and B. Okay, so we're gonna code along over here. Okay, so I'm gonna have you code along with me. The first thing we'll do is we're going to write the model, and we're going to write the model as a function. We're going to do it in this particular form, and you'll see that this becomes really handy later. We're going to make sure that our model takes in 2 arguments. One is P, which is a parameters dictionary. It should have keys W and B, which map to floating point numbers. And it should have taken another argument X. And what X is X valued for the function. Okay, cool, are we okay with that? And then what we'll do is return P of W times X plus P of B. Are we okay with this? Okay, so first things first, it's really important with JAX and AutoGrad that in your functions, especially the ones that you want to take the derivative with respect to, the parameters have to be the first argument. Because by default, grad takes derivatives with respect to the first argument. And so by convention, I sort of just make sure all of the child functions that are inside there also have the parameters as the first argument rather than the data as the first argument. You might see it in a different way, okay? We're going to initialize values of W and B. Okay, so down here, we're going to initialize W and B over there. I'm going to do a little bit of a cheating thing. If you read the JAX docs, you'll notice they really don't like us to use the NumPy random module, but that's okay. We'll use it for now. It works fine, but they have a different random number generating system, which is optimized for consistency across hardware. We're going to cheat for a little bit. Just use NumPy's plain vanilla NumPy random module. So we're going to draw one value from standard normal. And we're going to do the same for params of B. I noticed there's a little bit of an inconsistency between the instructor version and the student version. So that's actually good. We'll have to modify the function a little bit. We're going to define the loss function over here. This is the ingredient this is the function that we actually want to optimize, right? So what we're going to do is we're going to put params as the first argument. I'd like to invite you to modify the student version MSE loss, okay? It takes in 4 things. Model the parameters, which we want to differentiate with the function with respect to, loss with respect to, the model function, the data, and the X values, as well as the Y data, the true values. Are we okay so far? All right so far? We can get rid of this, right? So we get rid of that, get rid of that. Param model. And so then what is our estimates? Our estimates would be model of params with X, and that will execute the linear model up here, defined above. Are we okay with that? And what are we interested in returning? We're interested in returning the mean squared error. We've already defined the mean squared error function above, so let's take advantage of that. MSE of y, which is the true, against y estimate, which is the model predictions. Okay? How are we doing so far? All okay? Okay, great. So the next thing that we do is we create the gradient function for the mean squared error loss. All right? Okay? So let's do that. We'll call it dMSE loss. And that is grad of the MSE loss, right? And so now I'd like you all to write the training routine, which is that for loop right down below. So spend a minute or two and work on that. And if you get stuck, talk with your neighbors. And then execute the cell. And once you've finished execution, give me a bored look so that I know you're ready to move on. And I will ask for a thumbs up later. At the same time, I'm flashing up the answer, so if you are, both of you, you and your neighbor are stuck, both of you can look up and take a look at what you need to do. Okay, so how many of you have the optimization plot plotted below? Okay, we're gonna wait for the others to catch up, all right? One hint you might need to know. The function grad of p returns the same types as the function, dMSE loss returns the same types as MSE loss. So if you put in, a dictionary, dMSE loss returns a dictionary that contains the same structure as the first argument that you pass into MSE loss. That's the correct statement, okay? So if you pass in a dictionary into MSE loss, dMSE loss will return to you a dictionary that is keyed in exactly the same way as the dictionary params. And the only thing that is different is that the value will now be the gradient evaluated at that point in the function, okay? And so then you can actually take advantage of that to extract out the exact gradient and update your parameters dictionary, right? Probably that's the hint that y'all need. So how many of you are at this plot? Can you give me a thumbs up? Okay, we're approximately about at quorum. Okay, so we're gonna move on. As you can see, this is how we train a linear model by gradient descent, okay? And so what were the ingredients that we needed over here? I'm not gonna give the answer straight away. I'm gonna have you all talk with your neighbor for a minute or two. Talk with your neighbor and try to formulate for yourself a mental model of what the ingredients were that allowed you to do this. So write it down, type it out somewhere, talk with your neighbor. All right, I hear the chatter dying down. I think this is a good time to come back. Any volunteers? What in your mental model right now are the ingredients that we need?
In my mind, the first one would be like we need a model to optimize.
All right, so we need to have a model. Anybody else? What else do we need? Joanne?
Some sort of loss function.
Yeah. Okay. What property of that loss function do we need it to be? We need it to be differentiable. At the least, right? It must be differentiable. Now, when we talk about a model specification, it's not just the equation form, it is also a specification of which parameters we want to optimize, right? Okay, and what might be the final ingredient here? Pardon me? Step size. That is part of the optimization routine, right? Inside there, we need to know how many times we want to run the optimization routine. And at the same time, we need to know how big of a step size we need to take. Cool. We can end the class now. Sorry, just.
So grad underscore p, is that has the derivative with respect to the intercept and the derivative with respect to the slope w?
Yes. So just to clarify, for the benefit of those who are watching this on YouTube later, the question is, does grad of p have, which is in the notebooks, does grad of p, what is its data structure? It's a dictionary. And its keys are identical to the parameter dictionary that we pass into the loss function. And its values, however, are not the original values, but instead the derivative of the loss function with respect to each of those parameters. Okay? That's one of the really nice, powerful things about JAX and the AutoGrad system that these guys have built. You can actually take derivatives with respect to arbitrary data structures. It doesn't have to be dictionaries. It can be whole NumPy arrays. It can be dictionaries of lists, dictionaries of NumPy arrays. It's really, really powerful, okay? Cool. So jokes aside, not that we're going to end the tutorial here, but jokes aside, really that's the title of the workshop, right? Deep learning fundamentals requires that you have a forward model specification, a differentiable loss function, and an optimization routine. And you've witnessed it, all three ingredients with linear regression. And congratulations, we actually didn't need 2 hours to study linear regression. We only needed 1 hour and 10 minutes. All right, so what I'm going to do now is try to connect some of the ideas that we've done here into these pictures that you may have seen in the deep learning world, okay? This might take more than 15 minutes, so if you don't want to lose your binder session, make sure in between you execute something. Just run a cell or something like that, okay? But we're gonna use drawings to figure this out. Sorry. So we're gonna use drawings to illustrate this, and I think it's really powerful to see it done this way. These figures, by the way, are in the bottom of, if you scroll down a little bit, you'll see the same figures we're going to draw, but I think it's very helpful to draw it bit by bit so the layers show up. It's pun intended. Okay, so if we think about linear regression in matrix picture form, we start with some data. We multiply it by a weights. Oof. And we add a bias term. And that gives us our output y. Are we okay? Usually we have multiple rows, and that's what the ellipses in the boxes stand for. And just saying we don't have a single row, we have like a column vector of that data. Linear regression in higher dimensions, that is, let's say we have 4-dimensional inputs. Looks something like this. If we know that we have a single output y, the shape of our w's and b's lets us control how x gets transformed into y. So if we have a k by 4, k rows by 4 column x, what is the shape of w that we need? 4 comma 1. Because the result of this matrix multiplication is that guy by that guy. So we'll get k rows, but 1 column. And what do we need as a shape for the bias term? It would actually be only 1 comma. It's a single scalar in this particular case. And that's because if you take a k by 1 thing and you add k rows by 1 column and you add a scalar, the broadcasting works out such that you just added that bias term to all of the rows. Okay? So that's the shape. And what's the resultant shape out here for y? K comma 1. That's right. Okay? So knowing about these shapes, the shapes of our matrices, super important. And you'll see this later when we get to the deep neural network model at the last part of this tutorial. Okay? All right. This is one way of visualizing a neural network. One way of visualizing linear regression. I just slipped right there, Freudian slip. There is another way of visualizing linear regression, and that's by borrowing the neural diagrams that people have been drawing and have claimed is like a living neural being, right? No, it's not. It's just math. Okay, so we're going to draw this out. The same thing done, but now with a so-called neural diagram. So let's take the multiple linear regression example where we have 4 columns in our X data. We'll represent that as 4 inputs. And for consistency with the previous diagram, let's just add the ellipses to indicate we've got multiple rows of data. Okay? If we matrix multiply it against a 4 by 1 weights matrix, that actually looks something like this. Okay? These 4 red lines correspond, these 4 red lines over here, they correspond to the 4 entries inside there. Are we all right with that? Okay, so all it's saying is take this guy, let's call these I1, input 1, X1, just to be consistent here. Call it X1, X2, X3, X4, and then we have the weights, W1, W2, W3, and W4. This guy at the end will be X1, W1 plus X2, W2 plus X3, W3 plus X4, W4, which if you remember your linear algebra, looks exactly like X dot W, right? Exactly the same thing. So then what happens after that? We add in the bias term. And so this guy over here is the bias term. And then, we come back here and we get back our y. All right? Implicit in all of this is another function. And in this particular case, this is the identity function. What the identity function is, f of x returns x. So whatever input we put inside there, we just return. And so I'm going to put this y in parentheses and put this as the actual y. Okay? Are we okay with this? So far, so good? Yep. This is linear regression as a neural diagram, which is equivalent to a neural network with no hidden layers and an identity activation. Okay? Now I just let slip a few terms over there. You will see that's how people talk about neural nets. There's how many hidden layers, what are the activations and the likes. That terminology carries over exactly to linear regression, right? And so if you really wanted to spoof and If you were at a startup and you really wanted to raise money, you'd call your linear regression deep learning. Just not so deep, that's all. Okay? It's a single layer neural network with no hidden layers and an identity activation function. Throw that at them and your investors will give you money, right? No, they won't. Okay, so with this, at this point, well, congratulations. This is record time. 1 hour, 20 minutes. We covered both the code plus the neural diagrams. We're going to take a break now for about 10 minutes. I'm happy to answer questions. If you will all be kind enough, let me get a bit of water as well. And we'll come back here at, say, 9:25. I'm sorry, 9:35. 9:35, right? So we're a few minutes over. I'm just going to, before we continue, I want to clear up any lingering questions that we have, because if there's anything that's unclear with respect to the model ingredients for linear regression, then they will stay unclear, I'm pretty sure, when we talk about the parallels with other more complicated models. So are there any questions? I'll give you 30 seconds. Think about it. Write something down if you need to. Formulate your question. Are there any questions? Okay, up front.
So in the first example, when you gave the function, w squared plus 3w minus 5, you're taking the gradient of that and then stepping based on that. In the second example, something a little bit different is we actually define the loss function.
Yep.
And we're stepping down, taking the gradient of the loss.
Yep.
Could you explain that a little bit more as like why you have, in the first example was a function, we were taking the gradient, now we have a loss. We're taking the
Yep, yep. Okay, so just again for the benefit of YouTubers later, first example was all like this toy function f of w, right? And then the second, the substantial example was our linear regression loss. And you might be tempted to think that we should actually optimize the model, which is y equals mx plus c, right? But if we think about what we're trying to accomplish again, think back to the hand slider thing, right? What you were doing is you were not minimizing the linear model. What you're doing is you're minimizing the loss of the linear model with respect to the data. So therefore, we're taking the derivative with respect to the loss and not with respect to the model. Does that clear it up? Okay, cool, great. I think I saw another hand back there.
Yeah, on your optimization routine back under the code-along exercise.
Okay, so that's this one over here.
Yeah, so can you explain line by line what's happening there? I see we're talking about the progress bar, and then we're, yeah.
Yeah.
Understand like the multiple loops.
Yeah, no problem. Okay, so this was a common question, so I'm glad you raised it up. So again, just so that YouTube viewers can see this later, what exactly is going on here in this optimization routine? And I think the confusing part is this guy over here. Am I right? Right, okay, great. So to do this, we'll have to take a look at the data structures that we're interested in, okay? So DMSE loss is the function that returns the gradient evaluated, the gradient of the loss function evaluated at the current value of the parameters, all right? So that means it must return the same data structure as parameters. Params is a dictionary. Now if you add a cell below and you just put like execute params, you'll see that it is a dictionary. It's got a key value pair, okay? And one thing nice about a dictionary is we can actually iterate over the key value pair, and that's what we're doing in lines 44 and 45. So what we're doing in lines 44 and 45 is saying, let's update the value of the params, each of the params one at a time. So the first value that k takes on is actually the string w. So we're iterating over the key value pair. So the first value of k, it will be w. The first value of p will actually be this guy over here, because we're iterating over the params, the items. Now actually, you know what? I'll code this live. For k, p in grad p dot items, print k and p. Okay? And what it will print out, if you type this out on your own laptops, it will print out the first value of, the first value of b will be the first value of k will be the string b, and the first value of p will be, in this case, because we're iterating over grad p, it'll be the gradient of that. Does that make sense? Okay, so what we're doing here is then we're saying, in this case, we're doing it with params. So just to make the point clear, right, we have k and then the current value of params. We're going to update it with the grad value for that param, that exact parameter. All right, so we're doing an update step over here. And I wrote it this way to make it clear that params and grad p are of the identical data structures. Okay? Are we cool with that? Okay, cool. All right, any other questions before we move on?
Can I say this? So for this model, you can tackle with the first order, second order, third order. I mean, your model doesn't seem to be linear or non-linear. I mean, is that correct? I mean,
Which model?
the model, you go to the up, you just W times P.
Yes, this is a plain linear regression model.
Okay, so
Yeah.
is it we have the second order, third order? I mean,
So by second order and third order, that term can be overloaded depending on which context. Are you talking about second and third order gradients, or are you talking about second and third order terms?
second order, third order terms.
So okay, in this model, because we had just so by second and third order terms, also I just want to clarify, this refers to like the polynomial regression where you have x squared and x cubed terms, right? We can totally create a model that is, you know, if our x matrix, let's say our x matrix over here, x was not a scalar at this point, it's now a matrix that has got like 15 columns, of which the first few columns are just the raw x values, and then the rest of them are our second order x square and interaction terms. This same model can work. You just have to get the shapes of w and b correct, and the same model definition will work. Okay?
Where did you declare K or define K?
K is an iterator variable. So no, you don't have to. I'm not sure about the Python internals. Alex, do you have a response on this? Like iterator variables, we don't have to instantiate them first and declare them first, right? We just declare them in the loop header. Yeah. Okay, cool. Are we okay with that? Do you have anything to add? No? Okay, all right, cool.
I think I'm hearing a lot of confusion where people are confusing the expression in code with, you showed a one-dimensional visual
Yep,
for a parabola,
yep.
but we haven't seen the two-dimensional visual that would be like the projection down would be like the slope and the intercept.
Oh, okay.
I think that visual might help clear up some of the confusion.
Okay. Let's see. We've got time, so I'm going to do it. How many are okay reading Greek? Okay. Wow, I'm going to have to do this from memory live. The pressure's on. All right, so let's think about the mean squared error loss function. And we're not going to do it with NumPy, we're going to do it with just plain algebra. Right? This will show you what exactly we're optimizing. We're actually taking, in this case, a whole bunch of partial derivatives. And that's why I was hesitant to like live write this out. Because it's, for me, because I'm sort of weak on my algebra, that is, I'm very sloppy with algebra, so I'm going to have you all like make sure I don't write something wrong. It takes multiple lines of things to do what a seasoned mathematician would take a single liner to do, but we'll work through it. Okay, so MSE is defined as wx plus b minus y true whole thing squared. Right? That is the MSE function. We're going to call the MSE function f of x. just to make things, the symbols a little easier. So what are the things we need to be able to optimize? Well, before we optimize it, let's just expand the whole thing, okay? Wx plus b squared minus 2wx plus b y true plus y true squared. Are we okay with that? Nothing's wrong so far? Now, we still need to expand this term. So that's w square x square plus 2wxb plus b square minus 2wx y true minus 2b y true plus y true squared. Are we okay? So we need the derivative of this really expanded function with respect to not one parameter but two parameters, right? So we need to take now not derivatives but partial derivatives. So the partial derivative of f with respect to w would be 2x squared w plus 2xb minus 2xy true, and that's it, okay? And df by db would be 2wx plus 2b minus 2y true. Am I right? So far, so good. And we need to verify that this is the minima, right? So we do a second derivative. d2f by dw square is 2x square, and d2f by db square is 2. Are we okay so far? All right. Okay, I haven't made an algebra error just yet. Okay, good. Observe this guy. Is this always going to be greater than 0? Okay, so we can declare that as being greater than 0. And 2 is always greater than 0. Therefore, the loss function with respect to w is a smiley face of some kind. And the that's f of w comma x, right, is some smiley face, and f of b x is also some smiley face. Are we okay with this so far? Okay, so now I want to make sure, because I think you're asking about the visual part. What exactly is going on? What you would, now I'm hesitant to plot this live because I don't really know the three-dimensional Matplotlib API. But basically, if you think about it, I have a w-axis, and I have a b-axis, and I've taken partial derivatives with respect to those. This whole thing looks like a bowl, right? And so that's the visual that you'll want to keep in mind. And remember, this is not the linear model, right? This is not the linear. The linear model is just some function of x, but the loss function, what we're really interested in is that with respect to w and b. Right? And we're treating x as fixed and y true as fixed. Okay, does that answer the question?
Yeah, no, I was not even thinking about the details, I was just thinking that visual.
Right.
And the fact that you've got a two-dimensional gradient, you're applying both
Yes.
components in the code.
Yes.
With labels that you can't keep, people may have been confusing what's the labels for B and W.
Ah, right.
You're walking down the bowl and
Right. Right, exactly. So exactly that. And actually, you know what? I'm glad you brought it up, and that I'm glad that I misunderstood the question as well, because this one's always a great way to impress. Sorry, no, we're not out to impress the crowd. This is always like, so the fact that the intuition is a bowl, right, comes directly from the equations, right? And if you really push the algebra, then bingo, right? You see that there's, with respect to one axis, it's a smiley face. With respect to the orthogonal axis, it's a smiley face. Therefore, you put the two smiley faces together, you get a bowl. And that's a great way to think about the loss landscape. Now, this is why the mean squared error is such a nice thing, because you get the bowl. If you did mean absolute, I dare not go into the algebra, okay? But you get the point there, all right? Okay, any other questions before we move on?
Just one comment. I think there's a cost and actually the Hessian matrix need to be positive definite.
Okay,
It's more, yeah, you see the diagonal can contribute to know that positive definite.
right, right.
More rigorous.
There's more rigorous, yes. There's a more rigorous thing we can talk about afterwards, yes. Okay, anything else? Okay, if not, we're going to switch back to coding. Oh, no, apologies. No, we should actually come back to drawing because we're going to talk about logistic regression. All right, so let's talk a little bit about logistic regression, because that is the next thing that helps us build our intuition towards a deep learning model, right? We did linear regression for about an hour and a half, including all the questions. Let's now move on to logistic regression. Okay, so how many of you know the equation for logistic regression? Back there. In the yellow shirt. So, okay, all right, I won't embarrass anybody today. Logistic regression, visually, all we're doing, okay, is, sorry, screens are out. There we go. Cable was pulled. Let's see, let's wait for the screen to come back. Okay, logistic regression looks like this. I have my model, which is the x value. Sorry. And my y. I've got some data, and it happens that that data is split into two classes. Possibly 0 and 1. And what we're interested in doing is writing a model that lets us discriminate between these two classes as a function of the input x. And so we might write a sigmoid curve that looks something like that. Okay? This curve is what we would call the logistic function. And what's that logistic function look like? There's more than one form. We're going to stick with a simple one. L of x is 1 over 1 plus e to the negative x. Okay? Are we doing okay with that? And so that's basically the logistic equation. All right? Now, what's cool is that if we have our input data x, we can actually introduce shifts and biases in our curve, all right, to allow us to be able to model the fact that it may not be exactly this term over there. Right? Like this term has no optimizable parameters. So what we can do instead is take advantage of the fact that we have a linear model for x and then just do the transform on that. And that gives us a weight and a bias parameter that we can optimize, right? Now we can suddenly shift the curve left, right, and change how its slope looks like on the basis of those optimizable parameters. So what would this look like then? This would look something like this. You would have input data x, okay, you multiply it by your w, oops, wrong colors, So to keep the color consistent, we'll use that. Blue for the B. And then we'll do a logistic transform on the output. Yellow for that. Are we okay with this? All right, so really now we would have this whole equation would be expressed as 1 over 1 plus e to the negative wx plus b. And just to make sure nobody's confused, I'm going to change that thing up there. So if you were writing notes, make sure up here, the logistic form of the equation, you change the x to a z, right? Okay, so this becomes the equation that we can write as our forward model. And that gives us a few knobs that we can play around with, okay? So I'd like you to take a look at the interactive activity below. In your notebooks, we'll come back to that. And I'd like to ask you to play around with the two parameters w and b. And spend a minute or two, record your observations. What does w control and what does b control?
Yeah, so W changes the slope of the sigmoid part between the plateaus,
Yeah,
and then B just changes where the sigmoid part is.
the middle point of the curve. Yeah, okay. So as you look at it, as the magnitude of w increases, we have a sharper transition from 0 to 1. And as b changes, as b goes more negative, this whole thing shifts, the midpoint shifts to the right. And as b goes more positive, the midpoint of the curve shifts to the left. Right? So that's exactly the intuition. So now suddenly we have, with this model, we're able to, once again, optimize it with respect to data. Okay? So what I'd like you to go ahead and do now is follow the next section of the notebook. I'm going to give you about 10 to 15 minutes to follow it on your own, okay? And then we'll come back and we'll talk through the whole process, okay? So if you're used to using np.random, keep in mind JAX's NumPy wrapper doesn't have access to numpy.random because they have their own random module. So at the top of the notebook, I've already imported for you all npr for NumPy random, and then you can do your own random stuff, okay? Okay, so someone found a little bit of bug in the syntax. This loss function, it's negative of the whole thing inside here. All right, just so that there's no confusion. Okay, if you get up to line 29, the final thing that we want to do in line 30 is basically just keep track of the loss at each point, right? That's all we're doing there. Oh, how many of you got confused by the flatten and unflattener? Ignore that, like delete that line. My apologies. I should have done a finer check through on the student notebook. If you see it in the neural network example, you also can just ignore that. Okay. Quick conceptual question. In the logistic loss, if you only typed the thing inside the mean, then that would be, and you took the negative of that, you would get back a vector of values, right? Because you basically get one loss per data point. That would give you some issues when you're doing the optimization, right? Because the thing that we need at the end is like a scalar value. So want to make sure that you actually have some form of reduction inside here. So you either take the mean or you take the sum. Both of them are equivalent, okay? So that's really important. If you're stuck on that, this is like the key point, all right? So you always remember now, the loss function has to return a scalar with which we optimize with respect to all of the parameters underneath, all right? All right, in the interest of time, I'm gonna reblank, keep on coding for a little bit. I'm gonna reblank whatever I've written and live code with you all so you can follow along, okay? Okay. All right, so let's do this together. So first off, we're gonna go through this component by component. So once again, you get a feel for logistic regression, but you'll also hopefully see the parallels to what we did with linear regression. So first off, we have the logistic model, right? And the logistic model, as we wrote it out, consists basically of two steps. We do a linear transform first on our input data x, and then we do the logistic transform at the end of that. So to make that explicitly clear, we'll put P of W times X plus P of B. And then after that, we do the logistic transform, which is already defined above, and then we return that result. Are we okay with that so far? All right, so that's the logistic regression model. What about the loss function? Well, we're going to pass in the model into here. So the predictions are the model of P and X. And by the way, that should look identical to what we did for the linear regression thing, right? Like, it's just a generic model. Like, the predictions are really, that's all it is.
Do you need to use the logistic model that you made, or is that better?
Yes, we do, but we will pass that in later. We've specified the model. We'll specify the model as an argument, so then we can literally plug in any model that we want. We don't have to worry about which exact model it is. So we'll then return, now we won't return the preds, we'll return instead the logistic loss, and in this case, let's do the mean logistic loss across all samples. So it's minus np.mean, y times np.log of preds, okay, plus 1 minus y times np.log of 1 minus preds. Okay, we okay with that so far? All right, now we need the gradient of the loss function with respect to the parameters that we have. And then after that, we're going to start by defining starting guesses, starting points, guesses at what parameters we want. So you can do npr.random, or if you want to be a bit more principled, maybe npr.normal. There are actually even fancier ways of initializing weights, but I don't want to get into that today, because today is about the fundamentals. So you got that, and then we write our training loop. So we'll first get the gradient of the loss function evaluated at each of those parameters of interest. And then after that, we'll do the parameter update. Right? And then the final thing is, let's maybe keep track of the loss as we go over time. And this is a useful diagnostic plot for checking that you've got like convergence of the training loop. Okay? So we'll append the logistic loss evaluated at those params for the logistic model. Oops, this is over here, sorry. In line 26 on my screen, we will want to make sure that the model that's passed in is the logistic model. Okay? And why true is not defined? Maybe I forgot to run something above. Yeah. Cool, and now we have the training loop going. Everybody have the training loop going as well? Already done? Okay, your model should be fitting. Let's see. While that's running, let's talk a little bit about the loss function. So you'll notice for classification tasks, we wrote a different loss function, or we use a different loss function, and this one is the logistic loss, or the binary cross-entropy loss function, right? So let's think a little bit about what this loss function expresses and why it might be an appropriate loss for a classification task, all right? Y in the equation, so you can all see it on your own screens. Y is the actual class, that is whether it is 1 or 0. P is the predicted class. Sometimes people interpret that as the probability of being class 1 or, probability of being class 1. So now, let's think about like what happens to the loss or to the terms inside the loss function. So can you discuss amongst yourself the discussion questions on the notebooks? What happens to the term y log p when y is equal to 0 and y equals 1? And then the converse as well. What happens to both terms then when we've got something that's close but not exactly 1 or 0? So think about that. Talk with your neighbor for a minute. It's all in the notebook. It's all in the notebook. Okay, so do we have volunteers? What makes this equation usable as a loss function? Sorry, can you say louder?
It classifies as 1 or 0.
So it takes the true class 1 and 0. That's definitely for sure. And then what happens? So I want to think about like the predictions, right? Because everything about the loss hinges on the predictions. So if my true class is 1 and my predicted class is 0.97, so this is a thing that's like really close to 1 but not exactly 1. What happens to the 1 minus y term? There is a term that's 1 minus y. Y is equal to 1. So what happens to the 1 minus y term? It goes to 0. It goes away. So we can actually just completely ignore that. So then what happens? So one thing that's nice about this loss function is that if we know the class, we can ignore the other term, right? So if we know the class is 0, then we ignore the y term. And if we know the class is 1, then we ignore the 1 minus y term. So that's the first nice thing about this loss function. Here's the next one then. So if the predicted class is 1, okay, if the actual class is 1 and we predict something that's 0.97, so it's really close to 1 but not exactly 1. What happens to the term log of p? It goes towards 0. So we're actually pretty minimal. Close, and as we get closer to 1, it goes towards 0. And if p goes towards 0, what happens to the log of p term? Actually increases in magnitude. Okay, so that's a really great, and then you can see for yourself that the converse happens for the y equals 0 class. What happens to the 1 minus p term? It's the exact same behavior. Okay, so one thing important about this logistic regression example is that, by the way, everything we did for linear regression, we used the same machinery for logistic regression, the only difference being we changed the model spec and we also changed the loss function so that we can correctly solve for the problem at hand. Okay? So this is one of the nice things about knowing the components, because suddenly if we have a different problem that necessitates a different loss function, well, we'll just write the loss function and just make sure it's differentiable. That's it. We don't have to worry about the mechanics of trying to differentiate, try to differentiate this equation, right? I'm not going to. I'd rather have the computer do it for me. So that's the whole point of the automatic differentiation systems. Okay? Are we okay with this? I mean, you guys are awesome. You all are awesome. Like record time, 20 minutes we went through logistic regression. I think we can do this in 20 minutes for deep neural nets as well then. All right? Okay, so you should get something that looks like this. I'm going to skip that exercise that says, what if you did not round off the values? If you didn't round off the values, by the way, so we rounded off the values, right, to create 1, 0 classes. If we didn't round off the values, I'd say go home and check that out and see what happens if you do MSE versus mean squared error versus a logistic loss, right? For this part, for the sigmoid curve problem. And check for yourself, what changes? How does the optimization routine behave, right? How does the loss value behave? How does the loss landscape change? Okay, so we're gonna go on and talk about neural networks then. So I think given the pace that we're going, we're actually gonna build our own like little mini Keras for writing neural nets. It's doable, but we'll go through the internal meats and bones of like what exactly is going on inside a neural net here, okay? So over here today, we're only gonna talk about feed-forward neural networks because they have the most parallels to the linear and logistic regression models that we've written. And if you were to take a neural network that looks something like this, okay? How many of you have seen diagrams like this out there? Yeah, so neural networks are commonly drawn like this. I've actually drawn it a little bit more explicitly than most people will draw their neural nets, right? Most people will draw their neural nets excluding the B1 and tan-H part, assuming that those are always going to be there, right? Or they'll basically omit all of the, they'll omit the blue and the yellow or blue and orange components just for brevity, right? Because there's no so-called dimension change. What exactly is a neural network doing here? Well, underneath its core, it's math, right? Linear algebra, matrix multiplies, transforms, and that's all, right? That's all it is. So a neural network isn't living. A neural network is just math underneath the hood, right? So we're gonna implement something like this. Want to give you some terminology, okay, so that you can maybe hopefully connect some of the ideas here to things you'll read in blog posts and papers. There's this thing that we call activations, right? How many of you heard that term? So can you point to where the activations are in this neural diagram on the right-hand side? It's right after tan-H part, exactly. So what is this activation? This is the activation of the set of neurons, okay? Like just to borrow some terminology from neuroscience, is the activation of the set of neurons having passed the input data through these 3 transformations: the weight multiplication, the bias addition, and the nonlinearity term. We okay with that? So that's the first activation. And then what's the second activation? The thing right after the ReLU, which actually, if you think about it, is nothing more than just the output that we're predicting. So I've got this thing in my head that like academics always love to come up with new terms so that they can stake their flag in the ground and like say I belong to this field, and so we have jargon showing up as a result. That jargon maps to nothing more than what we just talked about, okay? That's what activations are. How many of you have heard the term dense layer? Yeah, where's the dense layer inside here? We got 2 of them, right? And why is it dense? It's dense only because we've got a full weight matrix multiplication. We're multiplying every input by the weight matrix, and we're not dropping, there's no sparsity inside there, so it's dense. Sorry, I had to do that. And so if we assume that the B1 and tan-H are, there's no shape transformation, then the term dense really just comes from this weight multiplication. So this whole transformation of W1, B1, tan-H gives you a dense matrix multiplication, which then gives you the activation out here, all right? And then we do it again. There's another dense matrix multiplication plus the bias term plus the nonlinearity, and then we have the output of interest. Okay, so then the next thing to think about is, I'm going to jump a little ahead and think about this in abstract first. If our how many of you have heard the ReLU function? Okay, the ReLU function is what we call the rectified linear unit. It is defined in two parts. If the function accepts a value x. Now, if x is negative, we return 0. And if x is positive, we return x. So it forms this flat line up to 0, and then a line, a y equals x line upwards outside of, above 0. Is the ReLU function appropriate if we have outputs, like our real data, are zeros and ones? Is that appropriate? No, exactly, because as we increase our x's, we're going to make predictions that are way beyond 0 and 1, right? So we're going to have a kind of a bad model if we have that. If we instead, what would we then swap this function for? The sigmoid function that we maybe just defined just now, right? Yeah, exactly. So we would do something like that. Okay, I wanted that in our heads before we go on to the next exercise, which is actually what we're going to write a neural network. But I'm not going to make you write a neural network in NumPy on your own. We'll pair code it. We'll code it together. We'll live code it together. So in this case, we're going to use some data, like real data this time, not simulated data anymore. It's data that's relevant to work that I've done. It's quantitative structure activity relationship modeling. It's basically machine learning and chemistry. Okay, and this data set is a public data set. It's available on the UCI machine learning repository. There's featureizations of a molecule, and then there's a classification task that's at hand where the output's just a 1 and 0. So you got a matrix of like about 40-something inputs, and you've got an output that is one column. So let's now talk about the shapes, okay? Let's talk about the shapes of our data, our parameters. If we've got 40 inputs over here, what is the shape of, what is at least one part of the shape of the weights matrix that we know of? It's got to have, if we got 40 columns, then the weights matrix has got to be 40 rows. And it's, how then do we define the next, like how many columns? For those of you who have touched a deep learning framework, how do you define your next layer's shapes? Go back.
However many features you have per sample.
Well, oh, that's the input, right? Yeah, but how about the output shape? Some number, some arbitrary number. Usually smaller number, a smaller number than the number of features that we have. So we might do something like input is 40, then output is 20. Like just halve the number of things. So we compress the information that's so-called learned by half. And then we might take that 20 and then do our logistic regression on top of it, right? So we'll go from 20 columns to like 1, or we might do another one, like do another reduction to 10 columns and do it again. So in this neural network, we're going to try it out where we only do a single hidden, oh, sorry, I forgot to mention one more piece of jargon. This layer, this activation over here, right after tan H, we call that a hidden layer. So, you know, linear regression is a neural network with no hidden layers, right? A real neural network, has hidden layers, right? And so why is it called hidden? It's because it's not part of the input or the output. It's sandwiched in between the input and the output, okay? So we can talk about, so I'm not against jargon. Jargon is helpful, but we gotta learn what they really map to. And so the hidden layers are a nice, compact, and convenient way of conveying the complexity of the model. If I have something that's got like one hidden layer, generally we expect it to be less complex than a model that has 15 to 200 hidden layers in between, okay? So just want to make sure people have that, you all have that terminology under. Okay, so let's load the data. And we'll code this together, where we'll implement a neural network in pure NumPy code. So we've defined up here, is everybody over here? This cell, code cell? All right, we'll talk through what's going on here. We've defined up here a noise function that just helps us, it's a convenience thing, right? So we don't have to type npr.normal. Sorry, if you could please change that npr.normal. All right. We've got defined a noise function over here that will just give us a matrix of numbers, random numbers from the normal distribution, defined by the size that we've passed in. So let's think about this guy over here. If I get x.shape, if you type x.shape, you'll notice there are 41 columns. So let's write arbitrarily a neural network model that sort of halves the number of input dimensions in the hidden layer and then just does a logistic regression at the end. All right? So this is all for convenience and simplicity's sake. So we'll start with noise. It's, and we'll pass in a tuple that is 41 by 20. So we've approximately halved the number of input dimensions. And that's the weights parameter, right? That's the shape that we need. So what is the shape of the bias parameter then that we need? We need something that's got 20 columns, right? So, sorry, we need a 20 unit bias vector, okay? And then now we're going to go from 20 dimensions in the hidden layer to our output, which is just a single dimension. So what's the shape of W2 that we need? 20 by 1, great. And what then is the shape of the second bias thing that we need? Yeah, 1 comma, right? Notice I'm being very explicit about the shapes, right? This is like a useful thing to know. What happens in the deep learning frameworks is generally this gets abstracted away for you. You don't have to worry about the shapes. However, if you don't know that there's matrix multiplies going underneath, you'll be left confused as to like, what is this magic number 41 and what's this magic number 20? So really what's going on is we're saying there's input 41 columns and there's output 20 columns. Then we take that again and say there's input 20 columns and then we output 1 column, okay? All right, so then we got the model. How do we write this neural network model? Well, let's talk about these as like in terms of activation. So we're going to write the activation from the first neural network layer is the dot product, so the linear transformation plus the bias term, mp dot dot of x with p of w1. We okay with that so far? And then we add p of b1 into that, okay? And then we're going to pass the whole thing through a nonlinearity function. One of the nonlinearity functions that's commonly used is the tanh function. That function is sigmoidal, except it's bounded from -1 to +1. All right? Are we okay with this so far? So we're writing. So by the way, if you are right now feeling in your head, this all looks kind of arbitrary. How do I know like what's the right is tanh the right thing? Is 20 the right shape for the middle layer? Like, you're not alone. A lot of this is arbitrary. And then a lot of machinery then gets invested in saying, well, let's just try everything from 41. So for the middle hidden layer, let's just try a grid search of like 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Right? Like, okay. And then let's also add in another grid, a dimension on that grid that says, I'll just try tanh and ReLU and Logistic and a few other nonlinearities in the middle without really justifying why. And that is exactly what how state of the art is obtained. Okay? No, I mean there's a lot more theoretical work. There's theoretical work that goes on, but like most day-to-day machine learning practice, it's a brute force search, plus all the heuristics you can think of. The few things that are principled are maybe you do some dimension reduction in the middle to do compression of the data, and then you put in like the correct activation function at the end, and everything else you sort of feel your way through it, right? you can tell I'm a little bit fatalistic about deep learning, not because I think it's not useful. I think it's extremely useful, and I wouldn't teach a tutorial on deep learning if I thought deep learning was not a thing, right? I'm a little fatalistic when it comes to like, let's try to get state-of-the-art results rather than let's just try to solve the problem at hand, right? Like that's, for me, solving the problem at hand beats out starting with a deep learning model. But we can talk about that later. Okay, so we talked about it just now. The output is a class 1, 0, right? So we need to, the last thing that we need is a logistic transformation of another linear thing as well. So we take A1, dot it against P of W2, and then we add P of B2, and then we basically return A2. Are we okay with that? So far, so good? All right, let's now write the logistic, let's now write the training loop. And by the way, that training loop looks identical to our first, yeah, it looks identical basically to our first logistic regression model, right? This training loop is written like that. Grad P is the logistic loss of params with the model, okay? We've got the exact model there. X dot values to make sure we're all dealing with NumPy arrays. Y dot values because X and Y were actually pandas data frames, okay? So do that. Then we'll do the parameter update. Minus grad P of K times 0.01. And we'll append the logistic loss again. And keep track of the loss over time. And we'll let that run. And if you all execute it, it should take a little bit of time. I should expect to hear a lot of laptop fans running shortly. It definitely does its thing for me. Let's borrow a book from the cooking shows where baking never takes 50 minutes. So training never takes more than 20 seconds because we have the pre-baked results out here. You should get a loss curve that looks something like this, okay? And then if you build the confusion matrix here, okay? If you build the confusion matrix here, it'll look something like that. Basically, black is like lower and red to beige is higher. And so we want the diagonals of the confusion matrix to be as high as possible and the off diagonals to be as low as possible, which then tells us we've got, okay, we got a model that at least works on our existing data. I intentionally said it that way because I left out a whole swath of things. We didn't do train test split. We didn't do cross-validation runs. More generally speaking, a lot of good machine learning practice I completely ignored here for the purpose of focusing on the fact that neural nets, deep neural nets, are nothing more than the same thing that you would write for logistic regression or linear model or some other model, right? Okay. While that's running, do we have questions?
Can you reiterate why you put the logistic around the A2?
Yeah, definitely. So the final activation corresponds to our predictions. And if our problem is a classification problem, we therefore then want our output activations to be bound between 0 and 1. If I put a different thing over there, if I put the identity function, which is just don't put anything, then we would get a linear transform and that would cause the outputs to range from basically negative infinity to positive infinity. And so the model we'd be fitting at the final layer is basically just this linear model where it's like it would be really, really flat if we had like x's that went beyond like we wouldn't be able to capture the bounds that it was like 0 and 1. We'd have a really bad model basically, okay? So it reinforces the point that the final layer has to make sense for the problem at hand. Now, if you've got a regression problem, and then a rule of thumb is just put the ReLU function or don't put any activation function at there, or like I put the identity activation function out there, just to make it explicit. It's the identity function. If you've got classification problems, play around, right? There's a bunch of those. And if you know that your problem actually ranges from -1 to +1, the thing you'll want to do is actually put the tanh function instead, right? That would be another option. So that last layer has to make sense for the problem that you're trying to solve. Okay? Did I answer the question?
Yep.
Cool.
So in logistic regression, what's the good way to sample from a hyperparameter, such as in this case data? I mean, we usually apply people say it's 0.5, but I mean, it could be that it depends on the situation, but just curious, what's the good way?
Okay, so the question is for classification problems, usually we set the threshold at 0.5 to decide that something should be 1 or 0, right? How do we decide whether that should be 0.8 or something else, right? I actually want to defer to Joanne, because Joanne's dealt with this before. She's an ex-colleague, so I want to defer to you on that. There's a whole calibration process that's involved. Do you want to speak to that?
So are we talking about the problem that I face with, most chemistry data? So we end up with data that basically exceed the limit of detection. So usually I end up with like large columns of data that are listed as greater than 100.
And we have no knowledge of the real value.
So we don't know what the value is. So this is biological assay data. So we're collecting something called IC50s, inhibitory concentration at 50%. So a drug will inhibit an enzyme. And sometimes we just hit the limit of detection, and I'm like, well, is it 100? Is it 1,000? Is it 10,000? I don't know. So the way we sometimes deal with that data is to just drop it out, or we can also set it to an arbitrarily high number. But
And then sometimes we'll build a classification model
yeah,
for that sort of thing. That's like common practice nowadays.
yeah.
But then how do we decide then, like, the probability? Is it at greater than 50, then we assign it 1, or is it greater than 90, then we assign 1? There must be a model calibration process, which I'm not aware of.
Yeah, so it's usually greater than 50.
Okay, so by common practice, people would say, like, just round it off, right? But then you can actually adjust that value to adjust for the, what we call precision and recall, right? Sometimes knowing the positives is more important than knowing the negatives, so you would adjust that accordingly, right? Sometimes the positive you don't care, so like you want to capture as much negatives as possible, so you shift it accordingly as well, right? So but that one definitely, yes, is a hyperparameter, and it is very problem specific.
So it's like the change of various chemistry components.
Yeah, so that's right. The definition of what counts as 1, what threshold to set to equate it to 1, that depends on the problem. All right? Any other questions? Okay. All right, so I have you all captive for just a little while. So I'm going to have Alex, I'm going to need some help here. We've reached basically the end of deep learning, the workshop. But I'm going to do one bonus thing for everybody. We're going to make keras. Right, a very ambitious goal. But before we do that, I'd like to get some feedback on how the tutorial went up to this point. And so there's some little cards up front. We need some help distributing them. I myself will go and help out. There's a QR code that you can use to fill out a feedback form on your phone, or if you go to the README on the GitHub repository, there's a link that you can click as well. There's a little feedback form, and I'd love to get some feedback from you before we go on to the final thing, which is like, how do we translate all of what we've written into like keras, okay? Sorry, I'm kind of nervous because this is literally in teaching this, the first time I've ever attempted this, to live code a keras prototype. Like, that's a tall order, right? Keras is very mature. It's got lots of tooling. What I'm really going to focus on is like the utilities that we'll need and sort of the structure of what how a deep learning framework might want to be organized. By the way, if you've done this once, you'll then realize, oh, that's all Keras is, and you actually can then go ahead and try to, if you need super custom things, you can actually write your own layers in either TensorFlow or PyTorch or whatever. Like the tutorial this afternoon probably will give you a hint on how to do that as well, right? But this is really how things might be. I just want to give you a flavor for how the frameworks are organized. I myself wrote my own framework for myself just to learn how a framework works, right? And so it's a useful exercise. At work, I do sometimes use that framework. It's if I write all my neural nets in JAX, then it's convenient for me to just pull that out and use it. Okay, so frameworks basically solve some pain points, and those pain points are the things that we want to like abstract away so that it's easier for us to write neural nets. That's all frameworks do. Okay, frameworks for WebViz do the same thing. Frameworks for laying out stuff on an HTML canvas do the same thing. They just make repetitive things not so repetitive. So you'll notice one of the repetitive pain points that we had here was like this guy. We have this pain point where it's so basically we had to manually specify shapes, and we're repeating the middle layer numbers like many times, right? Imagine if you have 4 or 5 or 6 layers in between. That would be kind of a painful thing to do. So what if we could have a function that we could call that looks something like this? Consecutive dense. Params is consecutive dense of 40, 20, 10, 1, right? And I think you might get where I'm headed with this. I only want to put in the input-output sort of shapes and just be done with it. So this is input, first hidden layer, second hidden layer, final output. Or in our example, we didn't have the 10, so it's 41 for input, 20 for the middle, and 1 for the end, right? So that's one of the things that Keras would abstract away with a different syntax, by the way. I'm not like building exact Keras. I'm just thinking about the things that we need to engineer to make a framework usable, right? So param shapes would be something like input to output column dimensions as a list, a sequential list of integers, okay? And then this returns P, a dictionary, with the appropriate nested structure. Okay, so we've got P, a dictionary, and that's what we're going to return. So if we have something like this, you'll notice we sort of have to iterate over pairs, consecutive pairs of these guys. So we'll start with 41 and 20, then we'll do 21 and 1, right? So we'll have to do a zip over sort of like a shifted list, basically. Okay, so this would be for input. Oh, sorry, that's restricted keyword. I don't want to like overwrite it. So what's a good name for this? Huh? Input underscore, output underscore. In zip shapes, we want the 0th element to the last element, excluding the last element, and shapes of 1 all the way to the end, right? So we're zipping over like a shifted list, basically. So now we need to create the parameter dictionary, and it's kind of tedious. So we're going to adopt a slightly different structure. We're going to make it a little bit more nested so that we can write a generic dense function that just operates on W and B, and we don't have to worry about like W1, W2, B1, B2, right? We don't have to worry about this much customization. So we'll do something like that. P. So the appropriate nested structure, I should probably define this a little bit as well. The param dict P will have something like this as its structure. we have that. We have layer 1, which is then a dictionary, which has W and NumPy, and then some random number, comma B, and then some random number. And then we'll do a next layer, W, some number, B, some random number, okay? So that's the sort of structure we're going for, okay? And because we have this integer indexing thing, or actually let's just do layer 0, layer 1, so that we follow Pythonic conventions. Because we have this integer indexing thing, we might want to put an enumerate inside, outside of that whole thing, okay? So now we get the index as we go along. We'll initialize the inner dictionary. Layer I, we'll take advantage of Python f strings, is a dictionary. Are we okay with that so far? All right, and then so P f layer I of W is noise with shape input output. Okay so far? Following? P of f of layer I of B is noise of just output shape. Are we okay? So far so good. We'll move on. Then I think what we do is return P. Okay. We should also probably put some defensive programming checks inside here. Every element inside shapes has to be an integer, right? So we'll raise an error if there are non-integers inside there. For I in shapes, if not is instance I int, then we'll raise value error, no, type error. I must be every element I in shapes is not an integer, okay? Right, so we'll raise an error that way. It's better than raising an assertion to, we have now explicit error types inside our code. Let me just make sure this function works. Let me put this up here, and we call it consecutive dense of 41, 20, and 1. Gives us a lot of stuff. Wow, yeah. Okay, so params is that. Params layer 0 and w.shape is 41 by 20. Yes. Cool. And B has the correct shape as well? Correct shape. Great. So now then we have layer 1. W has 20 by 1, right? And B has just 1, which is exactly how we wrote that. But now we did it in, what, 1 line of code rather than 4, right? So this is part of what a framework helps abstract away. You're not explicitly defining your weight and bias matrix shapes. Come to think of it, I should probably put this function inside the framework I wrote. Yeah, I've never written it for myself, so, well, thank you all for Okay, so we can actually take this and say params is now consecutive dense of that guy. Okay, are we okay?
What's the rationale for making it a dictionary instead of a list?
Yeah, so dictionaries, I guess we would use it because we can use strings and like convenient names to key in. I wouldn't have much other rationale beyond that. Okay, so then Next thing. So we've got our first utility function. We might put this in like utils.py, framework/utils.py. Are we okay with that? So next thing we might do is we might define, because we use so much dense matrix multiplication, it might be nice to have just a shorthand for that, right? Might be nice to have a shorthand for that. So let's define what a dense layer is. Well, if you look at what the dense layer is all about, it's really a dot product with a nonlinearity. So we'll sort of abstract the dot product with the nonlinearity inside a dense layer. So we'll do a activation is nonlinear. Well, let's be explicit. np dot of x, p of w, plus p of b. Okay, we're doing this generically, so there's no b1 and w1 inside there. It's just p and w, b and w, and then we return nonlinear can be, well, okay, so nonlinearity equals identity. And we'll do def identity of x, we return x. And that's the default. We'll set this as the default nonlinearity that we return. So then therefore, we just return nonlinearity of a. Okay, so far so good? So now we can actually change, and so this dense function would go in layers.py. Identity would go in actually, ironically, nonlinearities.py. Okay? We can now change the model definition to be a dense of, so for how would we do this? N layers. No, that's not very good either. Yeah, this is where like accessing the right thing in the right order really matters, right? So I'm going to cheat a little bit and take advantage of the fact that dictionaries in Python are ordered now.
That's where the list comes in.
Yeah, that's where the list does come in handy. I'm going to take advantage of the fact that Python dictionaries are now ordered by default, right? So, but you wouldn't like bank on this guarantee in a real framework. You would do some more rigorous things, okay? I'm going to cheat a little bit. So for kv in p.items, okay? A1 is a x is equal to dense of, just to be correct, params for layer params in that, dense of params with x, nonlin is equal to np.tanh, okay? Oh no, that would be wrong. Okay, we're not going to do a for loop, my bad, because we have too much changes in between. So we'll just do A1 is dense of params with x with a nonlinearity np.tanh, okay? And then A2 is a dense of params with A1, nonlin is logistic. Okay? So this is the new model definition. Are we following? We okay so far? Do you have questions?
I don't think the function like exercises were on the student notebook, at least. So it's just taking me a while to type.
Oh, this stuff?
Yeah.
I wrote them live just now.
Oh, okay.
Yeah, so if you want to copy it later, what I'll do is I'll actually take this part and move it into like a layers in numpy.ipynb so that you have sort of a reference for what's going on. But I'm not requiring that you copy it today.
Cool.
Yeah, don't worry about that. Okay, so this is like the second part of what we might do with a framework, right? We would write everything. We might abstract away commonly written math operations that are, a bit tedious. Okay, and actually this is p of layer 0 to be a bit more correct here. I would get an error. So, and that's P of layer 1. Okay? Yeah, so it's not params. We're not passing the whole parameter dictionary. We're passing in that particular layer's dictionary, for which then our dense layer can access the W and the B. Okay, do we have questions on this? All right. The final thing then is for me to just test whether this actually works. It's the time of, if the training loop doesn't, oh damn it, it failed. Oh right, so now we have to do a more complicated utility function for rewriting, for updating the parameters that are inside here. Okay, so, let's see. For layer params in what did I call it? Params.items, and then for kv in param.items. It's a little convoluted, but what we would want to do then is like define like a weights class that we can easily do the updates. We basically abstract this away, but I'm not going to do that right now. I'm not prepared to do that. I think I can do, let's see. Oh yeah, params layer k is params layer k minus grad p layer k. Yes! Well, there you go. That's it. So the thing trains. And we're not gonna fiddle around too much. But that, I hope that gives you a flavor of what goes on. I stopped it. Yeah, I hope that gives you a flavor on what frameworks are doing, right? And really what we've done at this tutorial is to peel back the layers, pun intended, and look at the internals of what's going on inside a deep learning framework, okay? How many of you are going to the TensorFlow one later? My hope is that this is really useful for you to understand whatever jargon that is TensorFlow specific, whatever jargon that is deep learning specific. My hope is that this will help you in the tutorial later, okay? Cool. So just to recap, that's whatever's on the whiteboard up there basically captures what we went through today. We studied linear regression for about an hour and a half, and that was, my hope is that that was a very productive time for you all to understand that whatever model that we have can basically be decomposed into a model, loss function, optimization routine. If we want to, and once we understand that there are these three components, model, loss function, optimization routine, we can write arbitrarily large models. Arbitrarily large models just means neural nets in this context. You can write neural nets if you can't fit a linear model, right? That's it. That's it. That's all it is, all right? Do you have any questions? All right, if we don't have any questions, we're done really early. I hope you have an enjoyable lunch. TensorFlow starts at 1:30. See you around the conference.